This is Richard Walker from Lucidate. Welcome to this 9th video on AI for computer vision. In the last video, we built an artificial EEG. Neuroscientists seek to understand and explain the capabilities of the brain. One of the tools that they use is the electroencephalogram, or more simply, EEG. This records electrical activity on the scalp. This activity represents the macroscopic activity of the brain. In an analogous way, we seek to understand our AI's capabilities by looking at the activations of neurons. We've trained networks with a series of convolutional layers to perform feature extraction. Following these are fully connected dense layers for classification. In the first few convolutional layers, visualization is straightforward. These layers produce spatial outputs that are easy to interpret as 2D images. Here we can see edges and aggregations of edges into lines, corners, and shapes. But at deeper layers of our classifier, it's not as easy to visualize the activations. We introduced a technique called t-SNE to address this issue. This technique allows us to cluster similar patterns of activations, as well as separating patterns of activations that are dissimilar. We can stimulate our network by showing it specific types of image. We can then record the activation patterns in our hidden layers. The t-SNE clustering and separation allows us to plot 2D and 3D charts. These charts show clusters of similar patterns of activations. This video divides into two sections. In the first, we will examine a series of t-SNE plots. These help us better understand the patterns of activations in our networks. In the second part, we will do a deep dive into the maths behind t-SNE. This will give us a better understanding of how the algorithm works and how to use it to our advantage. Let's remind ourselves why and how our EEG works. Let's start with a trained neural network that recognizes our color images. This is simplified to fit on our screen. The input layer contains 3072 neurons. We have 32 by 32 pixel images, each with a red, green, and blue channel. For our output layer, green represents high activation, what we're looking for, and red is low activations. For our hidden layers, white shows neurons with large activations and black low outputs. The weights between the neurons are represented in colour, with green being high weights and red low. The neuron that looks for cats is the 4th neuron in our hidden layer. The neuron that looks for ships is the 9th output neuron. These weights connecting our final hidden layer to our outputs are strong. To get a high activation in the 4th neuron in our output layer, which indicates a cat, we need the output of these neurons to be high. But that is not enough. We also have high values in these weights that are connected to our ship neuron in the hidden layer. To correctly classify this image as a cat and not a ship, we need the activations in these neurons to be low. By the same reasoning, there are other neurons that need to be low to avoid classifying this image as a dog, car, frog, or some other image. This gives rise to a characteristic pattern for the output of the final hidden layer. We need high activations in neurons that are multiplied by high weights connected to the 4th output neuron, and low activations elsewhere. If we work through the same example for the ship, we can see that we need the output of these neurons in the hidden layer to be low. Otherwise, the network might predict a cat. And we need the output of these neurons to be high. These are connected by high weights to neuron 9 in our output layer. All this together means we have very distinct patterns of activations in our hidden layers for different types of image. And the same is true as we look at other hidden layers. To generate this characteristic pattern in this layer, we will need a distinct pattern of activations in the preceding layer. This is frankly one of the great things about neural networks. While their operation in aggregate is a lot to get your head around, they are very easy to understand at a micro level. They're made up of very simple processing units, neurons, and some linear algebra, weight multiplication. So we can isolate the patterns of activations at each level. We can feed these activation vectors into our t-SNE machine to cluster activations that are similar. We can use t-SNE to show that our AI is even smarter than you think. Here is a 2D t-SNE plot of our digit classification. When we show the network 7s, we get a characteristic set of vectors that are clustered together here in green. When we show the network 4s, we also get a distinct cluster of activations. If we look closer at the 7s, we can see that there's a subcluster. If we look at each of the elements in the subcluster, we can see that this is made up of 7s with a slash through them, whereas the main branch is made up of 7s without the slash. If we look at a 3D t-SNE plot of the same data, we can see the same phenomenon. We now have volumes rather than areas where the similar activations are clustered. We can see here an arm of the constellation of 7s that represents the 7s with a slash through them. If we now look at a t-SNE plot of images of clothes, we can see another example of this. If we look at the activation cluster for bags, we can see another subcluster. Here we can see that the network has learned the difference between handbags with straps and clutch bags. This is a remarkable result. We haven't trained the network to differentiate between these representations of 7s or bags, yet it has figured out on its own that there's a difference and produces a slightly different activation. If these differences are important for your classification task, then you might consider training the network on relabeled data to make these distinctions explicit. We can also use our t-SNE activation cluster in conjunction with our confusion matrix. Here we see the confusion matrix for our best in-class digit detector. It incorrectly classifies these 5s as 3s. When you see which 5s are incorrectly identified, you might be tempted to cut the network a bit of a break. It would be very easy for humans to misread these digits too. Alongside the confusion matrix, we show the corresponding t-SNE plot, and we can identify a couple of the 5s that have been misclassified. A harder challenge than our monochrome digits and clothes is our colour images of vehicles and animals. Here we see the t-SNE plot of our best performing network that scored over 86% accuracy on the test data. We can see a diffuse area in the middle of the chart where the activations aren't distinct enough for the network to make up its mind. Away from this muddy area in the middle, we can see some strong clusters of activations. In pink on the right, we see the cluster that represents our ships. Closer to the middle, there's an image of a cat that is misclassified as a ship. It's likely that the strong angles and edges of the shelf were responsible for this error. Most of the cat images it saw in training were close-ups of cats. We can, of course, look at 3D t-SNE plots. If we zoom in here, we can see the cluster of activations that represent aircraft. Unsurprisingly, we see images of birds in this cluster. I'm not as fond of the t-SNE plots in 3D as I am in 2D. You can end up spinning around a lot and zooming in and out to bring the data into focus. But as this is 3D, and as you can quantify from the pop-up tooltips, you do get an extra dimension, which can help when training the network. How would we produce these t-SNE plots? I'll explain the maths and concepts behind the algorithm in the next few minutes. t-SNE performs dimensionality reduction. Frankly, much of AI involves reducing dimensionality. Our colour image classifier reduces an image of just over 3,000 pixels into a 10-element classification. Our eyes and brain do much the same thing, only far better. About 500 million photons hit the back of our optic nerve every second. We effortlessly reduce this to about 20 objects or concepts that we can deal with. t-SNE is good at clustering complicated information that has similar structure. Deep inside neural networks, we have layers whose activations are very similar for similar objects. When a neural network sees images of cats, specific patterns of neurons fire. A different pattern of neuron activation happens when the network sees images of ships. t-SNE can cluster these activations together on a chart. No matter how many neurons make up our activations, t-SNE will figure out which ones are similar and group them together. It does this using both statistics and calculus. We'll focus mainly on the statistics here. The calculus it uses is frankly familiar to us already. It uses gradient descent, which we covered when we looked at back propagation for neural networks. It does use a more complicated cost function than we use for back propagation, and we'll discuss that cost function shortly. If you'd like to review gradient descent, please watch videos 3 and 4 in this series. Let's look at a simple example. We'll use t-SNE to reduce data from a 3-dimensional bubble chart to a 2D map. Here are a set of points in 3D. We can see that they're clustered together in 3 distinct groups. We can color code each group so that we can more easily refer to them. Let's look at the red group and this red point in particular. We can calculate the distance from this point to each of its neighbours. We can also calculate the distance from this point to all the other points in both the yellow and the green groups. t-SNE first splits all the points into pairs, and it then seeks to quantify the question, how likely is each pair to be neighbours of one another? We can calculate the Euclidean distance between each pair of points. Points that are close are much more likely to be neighbours than points that are far away. So to convert these distances into probabilities, t-SNE uses the good old Gaussian distribution. You'll have an opportunity to influence the variance of this distribution by setting a parameter called perplexity. So more on that in a little while. So we could call this probability a measure of neighbourliness or closeness or proximity. Here we can see that the green and yellow points have a much lower neighbourliness score to our bright red point than the bright red point does to the other 2 red points. The next step of the t-SNE algorithm is to normalise this score for every point so that the neighbourly scores sum to 1. If we have n points, then we'll have n multiplied by n minus 1 pairs of points, as a point can't be a pair with itself. So with the 9 points in our example, we'll then have 72 pairs and hence 72 normalised neighbourliness scores. Here we see these 72 scores in an ordered matrix. We can ignore the leading diagonal, as this is just the distance of each point to itself. Ordering the scaled neighbourliness scores into a 2x2 matrix isn't a necessary step in the t-SNE algorithm, but I find it's useful to visualise the data in this grid. Ordering the axes means that the high scaled neighbourliness numbers are clustered around the leading diagonal, with low values elsewhere. For our lower dimensional visualisation, which we will from now on refer to as a map, we want to create a set of points that have the same scaled neighbourliness as our actual data in higher dimensions. t-SNE starts by randomly allocating points on a map, and we can calculate the pairwise distances in exactly the same way. We can also calculate the neighbourliness and the scaled neighbourliness for the pairs of points in our 2D map. t-SNE gives us a way of iteratively moving our points around in our 2D map. At the end of all the iteration, The scaled neighbourliness is the same in our map as in the original high dimensional data. We keep similar data clustered together and dissimilar data far apart. The trick in t-SNE is to use a different distribution to calculate the probabilities in our map than we do in our high dimensional space. For this, it uses the student's t distribution. The t distribution is very similar in shape to the Gaussian or normal distribution. It has a smaller peak but fatter tails, and it's these fat tails that help the model perform better and stop clusters all crowding together in the middle of the map. We'll show why shortly. The t in t-SNE indicates the use of the t distribution. Regular SNE, or stochastic neighbour embedding, uses a Gaussian distribution to calculate the probabilities for both the high dimensional data and our low D map. We now want to nudge our map points a little to get the map's scaled neighbourliness to resemble the scaled neighbourliness in the higher dimension. We'll use gradient descent for this, just as we did when training our neural network. When training our neural networks, we wanted our output vector to be as close to our data labels as possible. For t-SNE, we want something different. We want the distributions of our scaled neighbourliness in our high dimensional space and our low dimensional space to be as close as possible. A measure of similarity between two distributions is the Libra divergence. I'd not heard of this until I started diving into t-SNE. The equation is shown on your screen. We want to measure the divergence in the distributions between our high dimensional space P and our low dimensional map Q. The expansion of this formula is shown here. We can see that the KL divergence is 0 when P is identical to Q, as the logarithm of unity is 0. We want to nudge our map points around to get the value of our cost function as close to 0 as possible. Therefore, we need to differentiate C with respect to our map points, y, I. When we do that differentiation, we get a very simple and frankly elegant result. This takes the form shown on the screen. This equation for nudging our map points has a very intuitive mechanical analogy. We can break this equation down into three components. The first component is a switch. This switch will be positive if P is greater than Q and negative if Q is greater than P. The second component is a spring. A spring exerts a force proportional to how much the spring is displaced from its equilibrium. This force can be either attractive or repulsive. The third component is a magnet. This has a force proportional to the inverse square of the distance. It can also be attractive or repulsive depending on the polarity of the magnets. So an intuition is to envision all our points being connected by springs and magnets. Our switch will control whether the forces between points are repulsive or attractive. The size of each force will be in relation to the distance as well as 1 over the distance squared. If we look at the regular SNE derivative, which doesn't use the t distribution, we see a much simpler equation, but one without the magnet term. It's the presence of this magnet term that stops the points in the map bunching together. It will exert a strong repulsive force when dissimilar points get too close to one another. One final point that I promised to come back to is the choice of variance in the model for working out neighbourliness in our high dimensional space. In actual fact, you don't need to worry about providing the precise value. By instead supplying the number of close neighbours that you expect each point to have, the t-SNE algorithm will calculate the variance for you by solving the equation on the screen. The number that you supply goes by the name of perplexity. t-SNE is very robust to a broad range of perplexity values. Here are 4 t-SNE plots taken from our digits classifier. In the left of the screen, we see plots of our first classification layer. This is taking the outputs directly from our feature extractor and beginning the classification process. The second column shows our final classification layer, the layer immediately before our output layer. Looking at these plots, we can see the initial randomization of the data and then some structure start to form as the repulsive and attractive forces of the springs and magnets start to sort out the data. We can see clouds of clusters start to form of similar points, followed by these archipelagos of data. In the left-hand plots, taken from the first classification layer with 1024 neurons, we see much more dispersion. At this level in our network, our feature extractor has done a good job at pulling out the edges, lines and patterns, but there's still some work for the perceptron to do to classify these shapes as a type of image. In the right-hand plots, taken from the very final hidden layer with only 64 neurons, there's a lot less dispersion. At this layer, the network has more or less made up its mind about the classifications. At the initial classification layer, one can also see the differences between subspecies. The structure of the different types of 7 is clearly present. In the final hidden layer, these nuances are gone. The network has been strongly incentivized to find just 7s, not types of 7s. So it's responding correctly to the goals that it has been set. There are 3,500 data points in this set, roughly 350 for each digit. In the top row, the perplexity is set to 350. In the bottom row, the perplexity is 200. The perplexity values of 350 and 200 are in the right area for this data. What happens to these plots if we change the values of perplexity? Here we see the same plots as before, but with the perplexity set to 1000, which is too high, and 50, which is too low. Too high a value will increase the variance in our original distribution. This will make the neighbourliness scores of points that really are neighbours far too low. And at the same time, it will make the neighbourliness scores of points that aren't neighbours much, much too high. What difference does this make? Well, frankly, not that much. It's only a problem when the variance and perplexity are too high for points that are really very well differentiated. You can see this in the upper right-hand plot. This shows the final hidden layer of 64 neurons. The patterns here of neuron activation in response to specific digits is really well set. So telling t-SNE incorrectly that points that are close aren't as likely to be neighbours as they should be is a problem. This problem's made worse by the fact that we're lying to t-SNE and telling it that pairs of points that aren't neighbours really should be clustered closer. Despite this terrible advice to our t-SNE algorithm, it soldiers bravely on and is still able to find some structure in the data. This shows how robust t-SNE is to different perplexity values. Nevertheless, it's still wise to choose perplexity sensibly and, as ever, experiment with a range of values. We've looked at how we can use t-SNE to make the inner workings of our AI classifiers less mysterious. In the human brain, we see patterns of activation in response to specific images, concepts, and emotions. Specific neurons fire when we see specific things. So it is with our artificial neural networks. t-SNE gives us a way of visualizing these clusters on low-dimensional maps. This makes it simple for us to see these patterns of activations. We've looked at how the t-SNE algorithm works. It measures distances between pairs of points, assigns a probability to how likely they are to be neighbours, and then normalizes these probabilities. It then uses gradient descent on a 2D map to shuffle points around so that eventually the scaled probabilities in the 2D map are the same, or close enough, to the scaled probabilities of the original data. Over the past few videos, we've learned much about how neural networks are built, as well as how to train, visualize their results, and optimize them. We've also seen how we can use techniques like t-SNE to gain a better understanding of their activation patterns. In the next video, we'll see how we can use very sophisticated neural networks that have been developed by the world's largest technology companies, firms like Google, Microsoft, Tesla, and Facebook. We'll see how we can take these very powerful pre-trained networks and put them to use on our own projects. This is Richard Walker from Lucidate. Please join me in the next video where we'll see how easy it is to use pre-trained networks developed by some of the world's biggest firms.